Hey everybody. Let's do the stuff. Let's see here. There's the attendance as usual. Go ahead and fill it out when you have a chance. Let's see what else. There are lots of things to talk about. I looked at he posted homework recently. I've looked at it. It looks a lot of stuff. So I guess I should say, guys, have any questions either about the homework or just in general about what he's talking about in class? Because there are definitely lots of things we can talk about, but if you have specific things you want to see, happy to oblige. Or I can just start doing stuff. That's also a distinct possibility. Let's see. There was another thing I wanted to give you guys. Just as a reminder, there's also tutoring available online. Here's a link to that if you are looking for help, and that's another resource where students are tutoring in. Once again, here's the attendance. All right, well, if you guys have questions, certainly pipe up, but if you don't, I will start doing stuff. Question one, yeah, I was just going to do one. I was like, let's do one similar to one, is what I was literally thinking in my brain. So, I wonder, I have a question. No, that's fine. So let's say we have, I wonder what he did. Yeah, he did. Okay, fine. So let's say we have a function like that, but not exactly the same. Let's say we have x cubed. Let me see one thing. Sure. X cubed y plus 4y to the fifth equal to y plus xy plus 1. And we're assuming, and whenever you see some gobbledygook like this where you have x's and y's all mixed up together, your natural inclination should be to think, oh, we have an implicit differentiation question. We're assuming that y is a function of x, and we're going to differentiate like y is a function of x. So we're going to find, so you can write this thing down, you don't have to. So we're assuming y is some function of x, and we're going to find y prime, or dy dx, or whatever notation you want to use. He writes dy dx, I like to write y prime because it takes up less space. So here's anything we have to be extra careful about. I want to make this oh, sorry, I want to check. Sorry, one thing real quick here. Let me do one mathematical thing. 12. I'll make this a 9. It's not really that important, but it's not important. Okay, so I want to find y prime. Just for those of you joining, we're doing some implicit differentiation. Here's the attendance again. So when I differentiate this, I have to use the product rule. Derivative of x cubed is 3x squared times y, leave y alone, plus, now we leave x cubed alone. And what's the derivative of y?
Y prime.
Thanks, yeah. Or you could say dy dx. Or you could say it's the derivative of y, right? All those things are the same thing. All right, now, when we take the derivative of 4y to the fifth, we're going to have to use the chain rule. I have 4 times some stuff to the fifth power. And that derivative is, well, the 5 comes down, I get 20 times my stuff to the fourth power, but then I have to multiply by the derivative of that stuff. So what ends up happening whenever you're doing one of these implicit problems is whenever you take the derivative of something with a y, you always end up with a y prime. But the reason is because of the chain rule. We're saying, oh, the derivative of y to the fifth is 5y to the fourth times the derivative of y. So the 4 multiplies it. On the right-hand side, the derivative of y is y prime. The derivative of x times y, well, again, we're going to have to use the product rule. The derivative of x is 1. Now, some people ask why we don't write like x prime or something, and it's because we're differentiating with respect to x. So x is a function of x, but its derivative is just 1. Y is a function of x, and its derivative is y prime. So we get 1 times y plus x times the derivative of y. Some people like to say, instead of saying it's y prime, I think it's smarter to say it's y prime. Oh yeah, the derivative of y is just y prime. You could also say, well, the derivative of y is 1, but then you have to multiply by y prime, so you still get y prime. And then be careful, I've seen people do this before, which we know is wrong, because we know the derivative of 9 is actually what?
Zero?
I think you said 0, but it kind of sounded like 2, but it is 0. So that's the first step. That's taking the derivative of both sides of the equation. This is the only step that has any calculus involved. The rest of it's going to be all algebra work. So we need to, our pens here. So we need to look at all of the terms that have a y prime. We want to group all of those on the same side and all of the other things on the opposite side. Doesn't matter which side you pick. So I'm going to bring all my y primes to the left. So I'm going to have x cubed y prime plus 20y to the 4th y prime minus y prime minus xy prime equal to y on the right, and then I'm going to bring this over to the right as well, minus 3x squared y. Okay, now on the left hand side, the reason I brought all the y prime things to the left is so I could factor out a y prime. So if I factor out a y prime, I'm left with x cubed plus 20y to the 4th minus 1 minus x equal to y minus 3x squared y. Okay, now we're going to divide by this thing here to isolate y prime. So we're going to have y minus 3x squared y divided by all of this. X cubed plus 20y to the 4th minus 1 minus x. And that would be my derivative. So are there questions about this before we move on to the corresponding second part? I might left my water bottle open. One second, we'll be right back. Okay, so let me ask again. Are there any questions about what we did here? All right, well, let's look at the second part of this question. So the second part of the question is find the equation of the line tangent to the previous function, to the curve, because it's not technically a function. So I'm going to write it out again, even though it's kind of funny. So to the curve, x cubed by 4 to the 5th. Equal to y plus x plus 9. At the point, this side here, 2, 1. Yeah. So I'm going to find the equation of the tangent line. Oh, how did I get y prime? Okay, so let's go back to it. So we started with this equation. We differentiated both sides. We're assuming that y is a function of x. So we're saying, okay, here we use the product rule. Derivative of x cubed was 3x squared times y. And then the other way, right, we left the x cubed alone, and the derivative of y is just y. For this function here, we use the chain rule. We said, okay, we got 4 times y to the 5th. The derivative is 4 times 5 times my stuff to the 4th times the derivative of my stuff, which is 5y to the 4th times y prime. And then we simplify, we got 20y to the 4th. On the right-hand side, the derivative of y is just y prime. The derivative of y is the derivative of y, which we call y prime. Here we use the product rule. Derivative of x is 1 times y, and then x times the derivative of y is just y prime. And then the derivative of 9 is 0. So after we took the derivative of both sides, so what we did, we took the derivative of both sides, then we just simplified. We used algebra. We said, okay, well, I rewrote this so that all of the y prime things, which are underlined up here, are on the left, right? Subtract the y prime, subtract the x y prime. And all of the circle things, which don't have a y prime in them, are on the right. The y here and the minus the 3x over y. After that, the reason we brought all the y prime terms to the left is so we could factor out a y prime. So dividing out a y prime from each of these, I'm left with x cubed, 20y to the fourth, -1, negative x. And then finally, I divided both sides by this to end up with y minus 3x squared times y divided by all of this, x equals 20y to the fourth minus 1 minus x. So that's the process for finding y prime. And it's very similar kind of for all of these. Oh my God, the word just left my brain, for all of these implicit differentiation problems. So the second part of this is find the equation of tangent to the curve, the equation of the line tangent to the curve we had before, x cubed y plus 4y to the fourth equals y plus xy plus 10 at the point 2, 1. And so literally, we don't really have to do almost any work here. We've already done the hard part. We know that the point is 2, 1. We know that the derivative y prime is this mess over here, y minus 3x squared y divided by x cubed plus 20y to the fourth minus 1 minus x. So then we can plug in this point to the derivative to find the slope at that point. So the slope is going to be just, I'm going to plug in x equals 2 and y equals 1. So I get, let's see, 1 minus 3 times 2 squared times 1. I'm just plugging 1 here, 2 there, or 1 there. On the bottom, I get 2 cubed plus 20 times 1 to the fourth is just 1. 20 times 1 is just 20. Minus x minus 2. Sorry, minus 1 minus 2. And then we just simplify. So I get, let's see, 3 times 4 is 12. 1 minus 12 is negative 11. On the bottom, I get 8 plus 20, which is 28. Minus 3 is 25. So there's my slope. So then I just use the point and the slope to write the equation of the line. And I'm going to do it the way I like to do it, which is the point slope form. I'm going to say y minus the y coordinate, which is 1, equals the slope times x minus the x coordinate, which is 2. And maybe it's okay to leave it like that, or maybe we should solve for y. So y minus 1 equals negative 11 25ths x. And then negative 11 25ths times 2 is positive 22 25ths. And I'm going to add 1 to both sides. We get y equal to negative 11 25ths x. 1 is 25 25ths, and 25 25ths plus 22 25ths is 47 25ths. So you could probably, I think it's okay to write it like this, but if you don't think it's okay, you can write it like this. Questions about that? Let me give you guys another one because there's something, he didn't mention this in class, but I feel like this is worth knowing. So in this problem that he gave you, problems 1 and 2, right, which are problem 1 and 2 on the homework are very similar to what we just did. You had to find the derivative and then you had to plug in the points to find the slope. But sometimes people like to ask the question where you don't actually have to find the derivative. Here's the thing. Let's say we had some other reason. So I'm going to make it. So we have x cubed y squared minus y to the fourth equal to, let's see what I want here. I'm going to do, sure. Sorry, I just want to make sure this comes out right. X cubed y minus, let's not make it crazy, James, minus x squared. Sure, this should be fine. 1. Oh, I don't know. Sorry. One sec. So we're going to do the same sort of problem, kind of. I'm going to show you something different. So this problem was just going to be phrased as find the equation of the line tangent. When you hear the phrase tangent line, you should think, oh, I need to find the derivative using the slope of the tangent line. Find the equation of the line tangent to the above curve at the point 1, 2, which is kind of the same as before, but not quite. Before it was 2, 1. Okay, so here's what we're going to do. We're going to find the derivative kind of like we did before. At least the first step is going to be the same. So step 1, differentiate both sides. So, okay, this is going to be kind of gross. So why did I pick x cubed both times? Yeah, let's make this an x to the 4th just for fun. Sorry, no, it's not going to change things in the middle, but there we go. Okay, so differentiating, we've got a lot of product going on here. So you have the derivative of x cubed is 3x squared times y squared that I leave alone, plus then I flip it, I leave x cubed alone. And the derivative of y squared, or the derivative of some stuff squared, is 2 times my stuff times the derivative of my stuff. So that's going to be 2 times my stuff y times the derivative of my stuff, which is y prime. Minus the derivative of y to the 4th is 4 times y to the 3rd times the derivative of y. Again, y is a function of x. Every time we differentiate some function of y, we end up multiplying by the derivative of y. Equal to, okay, product rule here. The derivative of x to the 4th is 4x cubed times leave y alone, plus leave x to the 4th alone, multiply by the derivative of y, which is the derivative of y. Minus the derivative of x squared is 2x, minus 0 for the derivative of 13. I wouldn't write the minus 0 usually, but I just want to make sure you see that. Okay, now here's the thing. If you're not actually asked to find the derivative, but instead just asked to find the equation of the tangent line at one point, instead of going through the whole work of finding y prime, which would be kind of gross, right? Because it's all the algebra is always kind of gross, right? But all of these terms would have to come to one side, and all the other terms would have to go to the other side, which we may still do. Here's what I want to point out. If you're not explicitly asked to find the derivative, y prime or dy dx, or whatever he's calling it, if you're only being asked to find the equation of the tangent line, we only need 2 things. We only need a point, which we already have, and we only need a slope. So I need to find the slope, but I can find the slope by plugging in 1, 2 now or later. I can go through all the work like we did previously and find y prime, and then plug in x and y to figure out what the slope is. But who's to say I can't plug in x and y right now? I can. So if I plug in x equal to 1 and y equal to 2, let's see what happens. If x is 1, y is 2. So if x is 1, I get 3 times 1 squared is 1, 2 squared is 4, plus 1 cubed is 1, 2 times 2 is 4. Y prime still sticks around. Y prime is still just y prime. It's not x or y. We're not plugging in for it. Let's see. Sorry. Minus 4 times y is 2. So 4 times 2 cubed is 8. 4 times 8 times y prime equal to 4 times 1 times 2 plus 1 times y prime minus 2 times 1. That seems a lot better than doing all of this kind of work to solve for this, right? Bringing everything to the one side, factoring y prime, dividing what's left over. It's kind of a big old mess. I feel like this is a little bit nicer because look what happens. I'm just going to get numbers. So I get 12 plus 4y prime minus 32y prime equals 8 plus y prime minus 2. And then let's see, bringing on y, well, let's simplify a little more, I guess. All right, this is a 12 minus 28y prime equals 6 plus y prime. So add 28y prime to get 29y prime. Subtract 6. 12 minus 6 is 6. So y prime equals 6 over 29. And then we have our slope, 6 over 29. So then, probably fit it in here. We can write the equation of the tangent line as y minus the y coordinate, which is 2, equals the slope times x minus the x coordinate. And you can either leave it like that or you could solve it for y. I'm going to do it real quick here. So if I distribute this, I get 6 over 29x minus 6 over 29. Then I'm going to add 2, which is 58/29. So I'm going to have minus 6 over 29 plus 58 over 29. And that's going to become positive 52 over 29. So what I want to point out here is that if you're only asked to find the equation of the tangent line and you're not actually asked to find the derivative, you are perfectly allowed to plug in the point right after the step where you take the derivative of both sides. And then you can solve for y prime that way. We could also solve for y prime and find the derivative. Do you guys want me to do that? Should we go ahead and find the y prime for this in terms of x and y? Okay, yes. It's weird, like when I step closer, like the screen definitely like Zoom is trying to like catch different things when I get closer to this. So let's go ahead and, so I'm gonna erase this. I'll just do that. I'll copy this. It's a giant gross pain. Yeah. Okay. I do think we should also talk about some related rates today. So I think that's probably up next. Related rates also has to do with this chain rule stuff. Let's see, I've got 3x squared y squared. Let's just do it this way. 3x squared y squared plus x cubed 2y prime minus 4y cubed y prime equal to 4x cubed y plus x equals y prime minus 2x. And we are going to bring all of the things that have y prime. I think I'm missing one. Let's double check here. Nope, I'm not. Just crazy. Sorry, I circled them instead of underlining them. So we're going to bring all of these to the same side. If there's more of them on the left, let's bring them all to the left. So I have, and let's simplify this a little bit. This is going to be 2x cubed y prime minus 4y cubed y prime minus x to the 4th y prime equal to all of the other things brought to the other side. So 4x cubed y minus 2x minus 3x squared y squared. Then we're going to factor out, oh, by the way, just in case, there's the attendance form again. Make sure everybody else fills it out. Appreciate it. We're going to factor out y prime. So we're going to factor out y prime, and left is all the same stuff, just without the y prime. So we get 2x cubed y minus 4y cubed minus x to the 4th equal to still the same thing on the right. And then finally divide by this. So we get y prime equal to 4x cubed y minus 2x minus 3x squared y squared all over 2x cubed y minus 4y cubed minus x to the 4th. And provided I didn't make an algebra mistake, if we plug in the point 1, 2, we should get the slope 6 over 29. Let's see. So I plug in x equals 1, y equals 2. I get y prime evaluated at 1, 2 equal to, let's see. So I get 4 times 1 cubed is 1 times 2 minus 2 times 1 minus 3 times 1 squared times 2 squared over 2 times 1 cubed is 1 times 2 minus 4 times 2 cubed minus 1 to the 4th. So I end up with, let's see, 8 minus 2 is 6, minus 3 times 1 times 4 is minus 12. 6 minus 12 is negative 6. It's a good sign. On the bottom, I've got 4. This is 32. This is 1. The 4 minus 32 is negative 28. Minus 1 is negative 29. So I get 6 over 29, which is exactly what we have over here. So if you just have to find this over the tangent line, you don't actually find the derivative. I personally think it's easier to, right after you take the derivative, just plug in the numbers and then solve the y prime. Whereas here, I feel like this was more work, right? We take the derivative, then we solve the y prime, and then we plug in the numbers. It just feels a little more algebraically complex. Either way is fine. And sometimes you do have to do this if you're actually asked to find the derivative in terms of x and y, not just finding this over the tangent line. Okay. Let's see here. I might remember taking darker. Let's went a little bit. There. So let's see. Okay. So are there other questions about implicit, or should we move on to related rates? I'm going to move on to related rates unless there are other questions about implicit. I did post one video yesterday about related rates, a couple examples. I encourage you all to watch it. They're pretty fast examples. I think it's like, I don't know, 7 or 8 minutes maybe at the most. Might be less, I don't remember. So for related rates, the name really says it all. We're talking about 2 different rates that aren't related to each other. So basically you're saying, okay, this thing is changing, and you're asking how this other related thing is changing. An example similar to, not exactly what I did in the video. Let's see if this is good. So let's say, how do I phrase this? Yeah, so let's say we, sorry, I had, that's fine. Yeah, okay. So we drop a rock in a pond and we have circular ripples forming and they get bigger and bigger. Circular ripples form. And the radius of one ripple increases at a rate of, let's say, 7 feet per second. The question we want to ask is, how fast is the area of the circle enclosed by the ripple? I'm just going to area of the circle. How fast is the area of the circle increasing? Let's say 5 seconds after I drop the rope. Okay, so here's what we've got, right? We've got some circle, and it's getting bigger, right? So after 1 second, the radius is 7 feet. After 2 seconds, the radius is 14 feet. Right, so after 3 seconds, the radius is 21 feet. So the radius is increasing at 7 feet per second. The area is not increasing at a constant amount per second, right? Because look, from 7 for, I should have picked nicer numbers. I'm going to change this to make it a little bit nicer. Let's make it 10 feet per second, just so you can make it a little bit nicer. Sorry about that. So, okay, these are different now. Apologies. So after 1 second, it'd be 10 feet radius. After 2 seconds, it'd be 20 feet radius. After 3 seconds, it'd be a 30-foot radius. But the area here is pi times the radius squared, which is 100 pi. And the area here is pi times the radius squared, which is pi times 20 squared, which is 400 pi. And the area here is pi times 30 squared, which is 900 pi. And so if we look from second to second, The radius isn't increasing in a constant amount, right? From here to here, it increases by 300 pi. From here to here, it increases by 500 pi. And in the next second, it's going to increase from 900 pi to 1600 pi, which is an increase of 700 pi. So every second, it's increasing by a bigger amount each time. So the question I want to know is, how fast is it increasing when I get to the 5-second mark? Well, good question. So related rates problems, most of the time, although I will say the problem he asked in problem 3 doesn't really kind of follow this. Problem 4 definitely does. The kind of the process for solving a related rates question is kind of a 4-step process, maybe 5 steps. Sometimes the first step is draw a picture. Here, I don't think we really need to draw a picture. So the first step is to identify what's changing. What is changing? So here's what I see changing. The radius is definitely changing. So the radius is changing. And then I'm going to say, well, the rate is changing. What rate is the radius changing at? It's changing at a rate of 10 feet per second. So here's how I'm going to express that. And this is important. I'm going to say that dr dt, the rate of change of the radius with respect to time, is equal to 10 feet per second. Some length per time. Okay, I also know that the area of the circle is changing. And I know that I'm going to express that as dA dt, the rate of change of the area with respect to time. Now, I should point out there are definitely other things that are changing as well. The diameter is changing, the circumference is changing, but those aren't things that I either know already or want to know. So I try to limit my list to just things that are known or that I want to find out. Okay, once you have the things you know and the things you want to know, your job is to find an equation that relates the non-time variables. So I know the equation that relates the area of a circle and the radius of a circle. And most of the time, these problems is going to be some sort of geometry equation, like an area of a shape or a Pythagorean theorem or some similar triangle stuff. One of those things often comes into play. So the second thing is to find an equation relating the non-time variables. In this case, our equation is basic, right? It's just pi r squared. All right, here's the third part. And this part's where things are a little bit tricky. Actually, I'm going to give us a little more room here because operates the room. So I'm going to differentiate both sides of the equation. But I'm going to differentiate with respect to the time variable, because the area of the circle is getting bigger as time is increasing. So the area is a function of time. Likewise, the radius is getting bigger as time is increasing. The radius is a function of time. So when I differentiate this, I don't just get one, I get the derivative of A is the derivative of A, which is dA dt. All right, what's the derivative of r squared? Well, just like in implicit differentiation, where the derivative of y squared was 2 times y prime, the derivative of r squared, or some stuff squared, is 2 times the stuff times r prime, the derivative of the stuff, dr dt. Let me write something to help you maybe see this a little bit more clearly. What I could have written here to make this more obvious is that I really have area as a function of time equal to pi times radius as a function of time squared. And so when I differentiate this, another way I could write this is that, oh, the derivative on the left is a prime of t. Another way of writing that is dA dt. And the derivative on the right is pi times the derivative of some function squared is 2 times my function to the first, I'm not going to write, times the derivative of my function, right? Just using the chain rule. That's exactly this, just written with different notation. Okay, so very important. You find your equation relating to non-time variables, and then you take the derivative of both sides with respect to time. And what should usually happen, there's a couple cases where it doesn't, but almost all the time, the rate of change you know and the rate of change you want to know should show up in your equation. If you're not getting dA dt or dr dt there, you're not going to be able to find the thing you want to find. Okay. So then, after we differentiate both sides, we plug in what we know and solve for what we don't. So I know I want to know dA dt. I know it's equal to 2 pi times the rate. So what's the radius? Well, let's see if I can read the question. So circular pulse form, the radius increases at 10 feet per second. That's going to be dr dt, what's over there. How fast is the area of the circle increasing 5 seconds after I drop the rock? Okay, so if the radius has been increasing at 10 feet per second for 5 seconds, what is the radius? It's 50. Right? Every second it gets 10 feet larger and it happens for 5 seconds. So that's what's going in for R right there is 50. And then dr dt is the rate of change of the radius, which is 10 feet per second. And now when you multiply this out, the units should make sense. So multiply this out, I get 2 times 50 is 100, times 10 is 1,000, times pi. So I get 1,000 pi, and I get feet times feet per second, so I get feet squared per second, which is a logical or reasonable rate of change units-wise for an area, right? Area should be increasing at square feet per second, just like volume should be changing at cubic units per time. So there's one example of related rates problem. Let's do another, at least another. Related rates is, I would say, I don't want to make it like seem hard, but I will definitely mention it's usually something that people often struggle with because it can be challenging to wrap your head around. That said, with enough practice, it's not too terrible. Let's see, what do I want to do next? I want to do like at least 2 or maybe 3. If you want to do one like his cone problem, but I want to do, yeah, okay. Let's look at his problem 3 though. Sure. So I'm going to just make something up that seems kind of dumb, but whatever. So suppose x and y both depend on time, which is a typical assumption for any related rates problem. The things that are changing depend on time. And suppose I'm going to do other. We've taken the derivatives of trig functions, right? I know I did it in the video. He's done it in class, right? All the trig functions. Yes, no, maybe. Okay, good. Great. Then I feel perfectly reasonable to do this. So let's say x will depend on time, and I'm going to say that I always pick something stupid though. Let's be careful. Sure, I'll do that. So let's say, sorry, I'm looking at this question. Suppose y equals tangent of x, and I know that the rate of change of x. So I feel like, yeah. So I know that dx dt is equal to -7. I would probably write this out, so I would be less nice than he is being here. I would say, and instead of writing this, I would, and the rate of change of x with respect to time is -7. Those are words you could use to mean the same thing as dx dt equals -7. And then we're being asked to find dy dt when x, no, that can't be right. When x is equal to, sure, pi over 4. Okay, fun times. This isn't as bad as it looks. So here's what I've got. I've got y equal to tangent of x. Okay, here's the wrong next step. So watch this, but don't write it down. We're not going to say y prime equals secant squared of x. It's not wrong to say that, but it's not what we want. Because we have that y and x are both functions of time. I'm not, so this looks like I'm differentiating with respect to x. But I don't need to do that. I don't want to, I want to differentiate with respect to time. So here's what I'm going to do, and then I'll show you more steps. So I'm going to say, well, the derivative of y with respect to time is dy dt. The derivative of tangent of x with respect to time, well, the derivative of tangent of some stuff is secant squared of that stuff. And then I have to multiply by the derivative of the inside, which is dx dt. If you don't like the way this is notated, that's okay. You could also think of it like this. You say, oh, really, I have y as a function of time, right? Literally, we're told at the beginning y and x are functions of t. And it's equal to tangent of x, which is a function of time, x of t. And then if I differentiate, the derivative of y is y prime of t. The derivative tangent of some stuff is secant squared of that stuff times the derivative of that stuff. So really related rates are just an application of the chain rule. I feel like that looks kind of good. That says x of t. It looks terrible. I don't know what it right there. Apologies. Let me fix that. Sorry. It says x. Oh, I know. It's x of t, and then I close my parentheses. Sorry about that. So x of t times secant squared of x of t times x prime of t. All right, and now we have to plug what we know. So I say, well, I'm trying to find dy dt. I've got secant squared of x is pi over 4, and dx dt is -7. And then I'm just going to figure out what that is. So secant squared of pi over 4. Yeah. Well, I know that cosine of pi over 4 is root 2 over 2. So secant of pi over 4 is the reciprocal, which is 2 over root 2. But that's actually more complicated than it needs to be. 2 over root 2 is actually just the square root of 2. So I could say that it's really just the square root of 2, right? Because any number divided by its own square root is its own square root, or you rationalize. So I get square root of 2 squared times -7, which is going to be 2 times -7, which is -14. So when you've got things that are functions of t, whenever you're differentiating them, right, when I differentiate this tangent of x, I don't just say secant squared of x, I get secant squared of x times the derivative of x with respect to t because of the chain rule. Okay, let's look at a third one. We'll look at a cone one. Cones are funky. Cones often, although not always, have something kind of extra. I feel like the way he's written this cone problem, he's made it kind of, he's made it easier than I would make it. Yeah, he's just giving you the thing right off the bat. So I'm gonna, okay. Sure. I guess I don't need to make it harder than that. So I would make this harder, but I won't just because. So let's say we have something like this. So the height of a cone, no, I can't. So let's say we have a cone. This is way different than what I would do. Oh well. So sure. The height of a cone is 4 times the radius. And I don't really care which way I draw it. I usually draw my cones point down, whatever. Here's my cone. Here's my radius. Often when I do cone problems, I think about like filling them up with water and asking kind of like how the volume is changing as the, or how the height's changing as the volume increases at some rate. Whatever. That seems probably not necessary. We'll do that if we need to. What is the, if the radius of the cone, so the radius is growing at, let's say, 3 centimeters per second. Sure, why not? What's the rate of change of the cone's volume? So the rate of change of the volume of the cone. So whenever you're asked a related rates question, they're always going to ask you how something is changing at some particular moment. Like you can just see my mouth there, and it was not my face. Okay, oh, there I am. Okay. I'm sorry, something's getting a little crazy. So what is the rate of change of the cone line when the radius is, let's say 10 centimeters, even though the numbers might not be super nice here. All right, so even though he starts off by giving you the volume equation, I really, really encourage you to, before you write down the equation of the geometric shape, to write down the things that are changing and what they are. So I know that dr dt is equal to 3 centimeters per second. I want to know how the volume is changing, dv dt. It might be worth mentioning, although I don't actually think it is, if you know that the radius is increasing at 3 centimeters per second, and you know that the height is 4 times the radius, well, so if the height is 4 times the radius, we take the derivative of both sides, dh dt is 4 times dr dt. So dh dt is exactly 4 times 3 centimeters per second, so it's 12 centimeters per second. Or you could just say, well, the radius is increasing at 3 centimeters per second, and the height is 4 times that, so the height's increasing at 12 centimeters per second. It's totally valid. I don't think we need that, but it's worth writing down. Okay, so now we need the equation relating the variables that are changing, the non-time variables. And it's already given to us. It's volume equals 1/3 pi r squared h. So volume code. Now, for this kind of problem, when you're trying to find how things are changing, trying to take the derivative of both sides, we need volume to be a function of just the rate. I mean, yeah. we don't want to have two different variables here, right? That makes things complicated. So what we're going to do is, and he already kind of gave it to us, or we gave it to us, that the height is 4 times the radius. So before doing anything else, I'm going to rewrite this as the volume equals 1/3 pi times r squared times 4 times r. And so then we're going to get volume equals 4 times 1/3 is 4/3 pi r cubed, which coincidentally happens to be the volume of a sphere, but that's just a coincidence. All right, so now we differentiate both sides. So the derivative of volume is the derivative of volume, dv dt, and the derivative of 4/3 pi r cubed is 4/3 pi times the derivative of r cubed isn't just 3r squared, it's 3 times my stuff r squared times the derivative of r, which is dr dt. So now, simplify, I cancel a 3 here. You get dv dt equals pi times r squared times dr dt. And now we're going to plug in. So if I plug in, let's say I don't know dv dt, I know that dv dt equals pi times r is 10 centimeters. So I don't usually write the units in there. I'm going to not write the units, but then I'll plug them in so we can kind of see. So you get 10 centimeters squared, and then dr dt is 3 centimeters per second. So looking at this, I get 100 times 3 is 300 pi. So you get 300 pi. And if I pretended like I didn't plug my units in, right, if I'm just thinking, well, what should my units be? Well, I'm talking about how a volume is changing. So, oh yeah, the 4 canceled out. Oh no, it did not cancel out. I just forgot the 4. Thank you. So there should be a 4 there, which means it should be, 4 times pi times 10 squared times 3, which means it should be 1200 pi. Sorry about that. Thank you. Usually people are going to want you to write the correct units for these problems. And what I'll say is you can usually just know what they are without having to actually write them in. So I know here, since it's a volume changing, and since I've worked in centimeters for my length measurement and seconds for my time measurement, that the rate of change here should be centimeters cubed per second. Because it's a volume, which is always a cubic measurement, divided by whatever the time unit is. But you could also plug them in, right? If I plugged in centimeters here and I wrote centimeters per second here, you can say, oh, I've got centimeters squared times centimeters per second, which is centimeters cubed per second. So the units should always work out if things are being done correctly. All right, that's all we have time for today, but we can definitely look at more of the homework on Friday and other questions. We can certainly talk more about related rates, but there's also, there's also other stuff to look at. So we should probably look at the inverse derivative theorem thing and the other stuff he's talking about. So I'll see you guys on Friday. Make sure you fill out the attendance form if you didn't already. And take care.